You know, from a plucked guitar string to a skyscraper swaying in the wind, vibration is literally everywhere. But here's the thing. It's not just random chaos. It actually follows predictable rules. So the big question is, how can we predict it? Well, in this explainer, we're going to break down one of the most powerful tools for doing exactly that, the equilibrium method.
Before we get into any of the math, let's start with something we can all feel. Just picture this. You're the one on that bungee cord, just hanging there, perfectly still. Gravity's pulling you down, but the cord is pulling you up. And in that moment where those two forces are in perfect balance, you're not moving at all. That peaceful, motionless state, that's what we call static equilibrium, and it's our ground zero.
Now, this whole bungee cord idea, it's more than just a cool visual. It's actually the key. It's the thing that's going to unlock the core physics of vibration that we're about to dive into.
Okay, so let's use that bungee analogy to start putting some real physics terms to what's going on. We're going to move from that feeling of just hanging there to the actual science. The bungee jumper really helps us visualize these key ideas, and now we're going to start defining them so we can build our predictive model.
So, the specific kind of vibration we're zooming in on is called longitudinal vibration. It sounds fancy, but it's a really simple idea. Just like that bungee cord gets longer and shorter, it's any motion where something stretches and compresses along its main line. This is exactly what's happening in things like engine shafts, support columns, and, yep, our simple spring.
And the tool we're going to use to analyze all this is the equilibrium method. At its heart, it's just a direct application of Newton's second law. It basically says that the force that's making something accelerate is always in a tug-of-war with the forces that are trying to pull it back to its calm, resting spot.
Okay, this is a really crucial distinction to get. On one hand, you've got static equilibrium. That's our jumper just hanging there, totally still. The forces cancel each other out, zero motion. But then, on the other hand, there's dynamic equilibrium. This is what's happening during the bounce. The accelerating force of the mass is in a constant battle with the restoring force of the spring. It's a balanced fight for sure, but it's a fight that's in motion.
All right, it's time to build our master key. We're going to play detective here for a minute, following the clues from our analogy to piece together the single most important formula in all of vibration analysis. And we've got a clear, four-step roadmap to get us there. First, we look at the system when it's at rest. Then we disturb it. We move it. Third, we identify the new forces that wake up because of that movement. And finally, we apply our equilibrium principle to see what it all tells us.
So for steps 1 and 2, let's picture our system. We have a mass, m, hanging on a spring. Just its own weight stretches that spring out a little bit, a distance we'll call delta. That's our static equilibrium. Then we come in, we pull it down an extra distance, which we'll call x, and then we let go. And that's when the motion starts.
The instant we release it, step 3 kicks in. It's that dynamic tug of war. You've got the spring's powerful restoring force trying to pull the mass back up, and at the exact same time, you've got the mass's own inertia, its resistance to change, creating a downward accelerating force.
And now for the magic in step 4. When we write this all out as an equation, the accelerating force on one side and the total restoring force on the other, something really beautiful happens. That initial little stretch from the weight, our delta, it shows up on both sides of the equation, so it just completely cancels out. It vanishes.
And this is what we're left with, the fundamental equation of motion. It's so elegant. All it says is that the entire vibration is just a pure relationship between the mass times its acceleration and a spring's stiffness times its displacement. That's the whole story, right there in that little equation.
So, this elegant equation, it's our key. And now we're going to use it to unlock what we've been after all along, the system's natural frequency. This is where the predictive power is.
So how do we solve it? Well, here's the great part. We don't have to reinvent the wheel. Physicists figured this out a long time ago. Look at our equation on the left. Now look at the standard textbook equation for something called simple harmonic motion on the right. They're almost identical, and we can use that to our advantage.
Because those two patterns match up so well, we basically get to steal the answer. We can directly pull out these simple, powerful formulas. And as you can see, the natural frequency, the thing we want to predict, can be calculated with nothing more than the system's mass, m, and its stiffness, k. This is the heart of our predictive power.
All right, enough theory. Let's see how this actually works in practice. We're going to take these formulas we just uncovered and put them to work on a real-deal engineering problem to see just how useful they are.
So here's our scenario. We have a 5 kilogram mass,
But instead of just one spring, it's being held up by 3 different springs, all working together side by side. The question is, if we disturb this system, how fast is it going to vibrate?
We can knock this out in 3 clean stages. First, since the springs are all working together in parallel, we just add up their individual stiffness values to get one total or equivalent stiffness. Next, we plug that total stiffness into our formula for circular frequency. And finally, we do a quick conversion to get the natural frequency in hertz.
So, we run the numbers, add up the stiffness to get 5,000, divide that by the 5 kilogram mass, take the square root, and then divide by 2 pi. And there it is. The system will vibrate back and forth 5.03 times every single second. A clear, precise prediction, all thanks to our equilibrium method.
So think about that. In just a few minutes, we went from a person on a bungee cord all the way to deriving a fundamental equation and using it to solve a real problem. And this simple relationship between mass and stiffness, it doesn't just apply to some block on a spring. It governs the vibration of bridges, the hum of engine shafts, the sway of skyscrapers. Which leaves you with one last question to think about. What other vibrating systems are all around us secretly dancing to this exact same fundamental rule?